Alright, just a short little video to help you guys do this online assignment. So, you're going to go to this physics classroom site. This should be here. It's going to be one of those interactive labs, not a concept builder. And it should take you to... Oh, excuse me. See if I can pop this out here. To this site. And we see here. So let's see. We have this is called stopping distance. Now, make sure that you guys understand we're not doing the lab that comes with this activity. I kind of made my own on this one. So by now you should have gotten a handout that looks. The first page looks like this, and there's a second page that the questions continue on. So you've got this big chart here. But before we start breaking out what we're doing this big chart, let's just look at what the website is. Okay, so here we've got a hill, okay, and we can put our cart at different heights that we see down here, okay, different height. Remember that height determines what our potential energy is. We're going to hit release here. This is going to release. It's going to roll down this hill. It's going to move through this photo gate, run into this box, and that's going to stop after a certain distance. Okay, so let's think about all the energy transfers that are happening here. It's not moving, so no kinetic energy, and it's all potential energy. As it rolls down the hill, that potential energy turns into kinetic energy. At the very bottom of the hill, it's all kinetic energy. And it moves through the photo gate, which when it does that, a speed will come up here. So we can hit release, it's going to fall, move through this like motion sensor, so it tells you what the speed was right there, and you then get to see how much distance the object moves. So here, so once it ran into the box, it went a distance of each of these big squares is 10 centimeters. So it went from 1, 2, 3, 4, almost 50 centimeters using our key here. So I'm using the front of the box here as my edge, so I would say about maybe 48 centimeters is how far it went after there. So there's a lot of transfers of energy happening here. Potential to kinetic, then has all that kinetic energy, and then friction dissipates all of that kinetic energy. It does negative work on it. So what we're going to look at is not just the energy transfer, but some of the negative work that's done. Okay, there's negative work done on the hill. There is friction on the hill, so there's friction there, and that's one of the things you're going to calculate. And then there's more friction down here that ultimately slows it down. Okay, so before I jump over to your worksheets, let's see if I can get both of these things showing up at the same time here. Almost, but not quite. So, if you're looking at the chart, okay, so a lot of these numbers, because it looks like there's a lot of information here, but it's really not that bad. So potential energy at the top of the ramp. Okay, we know how to find potential energy at the top of the ramp. mgh, mass times gravity times height. So just think of that as mgh initial. We're using 1 kilogram as our mass. Okay, and I even tell you what heights to use for each of these different trials. Okay, these are in centimeters, but remember that when you enter them into your equations, they should be in meters. So move this decimal place over 2 spots. So remember, 10 centimeters is 0.1 meters, 20 centimeters is 0.2 meters, and so on. That will get you your answers in joules. So first one, real easy. So let's just see here. So I did 40 centimeters, so we'll just jump to that trial. Okay, so that was just 1 times 0.4 times 9.8. So you just wind up with 0.4 times 9.8 So that gets me 3.92 joules. Okay, so PE final at the bottom. Pretty simple. We lost all of our height at the bottom. So what's that going to be? 0. That's going to kind of be the same in each. Now, why do I have both these columns there? To see the change. We went from this to that. So, what was my change in potential energy? How much did my potential... I went from this to that. So, what goes on there? We went from 0 to 3.92, so my change was negative 3.92. Next one, KE initial. I'm going to zoom this up real big so you guys can see a little bit better here. So at the release, what was my kinetic energy? It started from rest, so it was 0, right? And my kinetic energy final at the bottom of the ramp, that's informed by my kinetic energy equation, which is 1/2 mv squared. Okay, so 1/2 m is 0.5 times v squared. The v it gave me was 2.42. 2.42. So 2.42 squared. I'll plug that in my calculator here. 2.42 times 2.42. 5.85 times 0.5. So that gives me 2.92. I'll round it 2.93 joules of kinetic energy. So how did my kinetic energy change? I went from 0 joules to 2.93 joules. So I had a gain, positive 2.93 joules. So see, this is getting pretty simple. So, now this one's the one you got to think a little bit. This is the concept I really want you to understand. This last column before the black line says, the work done by friction on the ramp. We started with this much potential energy. We lost all of it. And we wound up with this much kinetic energy. 2.93 joules. What happened to the rest of it? We had all of this energy. We had positive 3.92 joules. We lost it all, but energy always has to go somewhere. Oh, well, it was falling, so it turned into kinetic energy. Well, it did, but why didn't all of it? That's because there was friction. So how much friction, how much work did friction do? The work done by friction is how much of this energy we lost by the time we got to here. Okay, which is, if you subtract those two, is 0.99 joules. Or rather, negative 0.99 joules. We went from 3.92 to 2.93. The difference between these two numbers, between your final kinetic energy and your initial potential energy. If I just write this out, you know, the conservation of mechanical energy equation says KE initial plus PE initial is equal to KE final plus PE final when there's a closed system. But if there's not a closed system, then the work done by friction has to get factored in. Like that. You can write this on your sheet if you want. Okay. I'm going to pause this to put some... So here's our big equation. This is conservation of mechanical energy when there's an outside force. If there's no outside forces, there's no outside work being done, the whole thing just looks like this in parentheses. You don't have to worry about this. You don't have to worry about that guy. The sum of these two is always going to be the same. But when there's friction involved, you have to factor that in. So how do we get these two sides equal to each other? The work done by friction, you know, in this particular problem, and really all the problems on here, your KE initial is 0, so that cancels out. Your PE final is 0, so that cancels out. Now, if there was no friction, your PE initial equals your KE final. The final being at the bottom of the ramp. Okay, we're doing this in two different parts here. But there is friction on the ramp, so that is the case. And you solve this algebraically, and you solve this for the work done by friction, you wind up getting PE initial minus KE final, which is exactly what you did. PE initial minus KE final. Sorry, I just realized why I wasn't getting a negative there. This should initially be on the other side of this equation. So solving that, for the work done by friction, it winds up being KE final minus P initial. And that's how you get the negative here. So this should always wind up being a negative number. And again, back up here, I'll put up what the original equation should be, is that we had a KE initial there. Plus PE final. And really, everything on this page winds up boiling down to this equation. But we do it twice for each trial. Okay, so this lab's going to take a day or two, but it really kind of sums up, a lot of different things that we're talking about all at the same time. Okay, so the work done, this is the work done by friction, initial KE, initial PE, and so on. But remember, there is no KE initial, so that cancels. There is no PE final when we're on the ramp. Okay, so that's the first half. So we've only talked about only up to the first half of what's going on here. So if I make this big again, so remember the cart was up here, rolled through here, at the bottom of the hill was 2.42, then it moved from point A to point B. So I said that before it stopped, it encountered, it moved a distance of 10, 20, 30, 40, we're going to say 48 centimeters. 48 centimeters, when we record that on here, that it needs to be in meters, so 48 centimeters is 0.48 meters. Pre-collision speed, that's the speed that we used over here. So that's at 2.42 speed there. So that's, I know I didn't have a slot for it over here, but that's the same speed we used over here. It was the final speed on this side, but it winds up being the initial speed over here. Okay, so it was moving this fast, 2.42 meters per second. And it ran that box, then it skid, and friction slowed it down. So before those two things collided, they had an initial kinetic energy. And that initial kinetic energy here is the same as the final kinetic energy over there. So that makes life real simple. 2.93 joules. Because we're talking about the same thing. We're just splitting it. So the final situation is at the bottom of the hill. So the final over here is the initial over here. So that's 2.93. KE final when stopped, that's a dumb question. What's the KE when something's stopped? It's 0. So again, what is our change? Change is always final minus initial. So for while we're on flat ground, the change in kinetic energy this time was 2.93 joules, negative 2.93 joules. We lost 2.93 joules. Okay, so the work total is the change in kinetic energy. It's asking you the same thing. Remember, the work energy theorem said, in effect, that work is equal to a change sorry, a second. That was awkward inserting special characters. But work is equal to change in kinetic energy. That's the work energy theorem. That's the whole idea right there. So you found the change in kinetic energy. The work total is the same value. 2.93 joules. And what did that work? Friction did. So again, it's the same answer, 2.93 joules. Friction did that work. Okay. Now this is a little bit redundant, but you need to understand that these values are equal to the same thing. And the important part is that mostly for each of these other trials, the process is mostly repeated. So hopefully you've been following along, because you're literally going to do the exact same things I'm doing, but for all the different trials. But the point is to understand why we're getting the answers that you do, because that's something that's going to come up on a quiz or a test that you guys are going to have to do on your own. Okay, so we're almost done with this slot in the table. So we have the work done by friction. So, work done by friction, work done by anything, is equal to W, the work, is equal to F times D. But it's friction doing the work, so it's the force of kinetic friction, Fk, times D. Let's make that a subscript real quick. Friction is the force, is the F, and the F times D. So we have the work total, that's W. I'm just going to get rid of this term since we've modified it. And solving that equation to solve for the force of friction, it's just going to be the total work divided by the distance that the work was done over. So again, just doing the algebra there, W divided by D now. So to get this answer, it's just going to be the negative 2.93 divided by the skid distance, 0.48. So that gives us negative 6.1 newtons of force. That's that one. And then the last column, it asks you to find the coefficient of friction while it was skidding between the box or whatever it was and the ground. And you guys got to remember a little bit back into what we did previously in previous chapters. Remember that our friction equation, Fk, is equal to mu k. So if you remember our equation for friction, let me just make this a little bit bigger for everybody. The force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. So mu k here, that's this guy, mu k. So we just found the force of kinetic friction, and we have to solve for this. Moving this equation around to solve for the coefficient of friction, we get this equation here. Mu k is equal to Fn over Fk. Remember, Fn is the normal force. The normal force, right? That's that support force of the ground upwards on an object. That force, when we're on a horizontal surface, we're not accelerating up or down, is just going to equal to the weight of the object. The weight of the object, if you remember, is found by just doing m times g. So to solve for this last step, to find out what that coefficient is, we get mg, the weight of the object, over Fk. Now for this particular object, stupid subscript screwing everything up, the mass is 1, gravity is 9.8, so we just wind up with 9.8 divided by 6.1. We can just ignore the negative there. Notice I transposed the equation there. It should be Fk over Fn, not Fn over Fk. So make sure you have that. That's moving this around to solve for mu k. It's Fk over Fn. And the normal force, as we said, horizontal surface, not accelerating up or down, just equal to the weight of the object. So for this last step, Fk, which we already solved for, is 6.1. We can just omit the negative. And that's divided by 9.8, which is the mass, 1, times the acceleration of gravity, 9.8. And again, we can omit the negative there. And that gives us 0.62. It's kind of a high coefficient value, but it stops it pretty rapidly by increasing the amount of friction. So it should be a high value. But double check yourself on each of these. This number should never be higher than 1. It should likely I don't know if we'll wind up being the exact same value, but it should at least be within the same range on all of these. Okay, so you're going to try this for each of the different heights and follow the corresponding questions. Okay, now that I've kind of walked you through one example of it, what exactly to do shouldn't be too hard, but you need to understand why. Okay, we're in two different parts here, two different parts of the example. You know, we go back to point 4. We started here. We had potential energy. Potential energy turned into kinetic energy. Should have been all of it, but we lost some of that energy due to friction on the way down. The speed here then transferred into this box, which had a lot more friction, slowed it down rapidly. Okay, so we're learning about conservation of mechanical energy. We're learning about negative work. We're relearning about friction and how friction contributes to negative work, as well as using all of the different equations that we've learned. But pretty much this equation is informing this entire exercise. If there is no friction, if there's no outside forces, this guy here, this term would be totally omitted. It would, not be there. K initial plus P initial is equal to K final plus P final. No energy would go anywhere we don't want it to go. But there is, of course, friction there, as there is in real life. So we have to consider it. But this equation whittles down to a lot less in each instance. So copy that. Paste it down here. But once we cancel out things, we have no initial kinetic energy. We have no final potential energy. So this initial equation, and this is just for this first part, because that's the part where it's falling, to this. Potential energy lost some of its energy to friction. There's negative work done on it. Here's our final kinetic energy. And that's here. The final kinetic energy here is the initial kinetic energy over here. So I took you through a whole set of trials. All of them are pretty much done the exact same way. But don't just repeat what I did. Understand what I did. And understand how this work relates to these changes in energies. So hopefully that's enough information. Fill out that chart entirely. Again, you can kind of double check yourself. The force of friction should always wind up being a negative value. The coefficient of friction should always wind up being a number between 0 and 1. Probably a number very close to this, if not that exact same number each time. Finish all those, answer the questions based on your data and what we talked about. It should probably take you the rest of this period and maybe even into the next day a little bit. So good luck, and have at it.